Okay, so as promised, we're going to 11.2. We've done 10.1, 11.1, 10.2, and now 11.2. So we're going to take a look at the hypothesis test for the difference between two proportions. So let's start from the beginning here, and we're going to take a look at performing hypothesis tests for the difference between two proportions using the p-value method, and perform a hypothesis test for the difference between two proportions using the critical value method. So General Social Survey took a poll that asked 350 employed people aged 25 to 40 whether they used a computer at work, and 259 said they did. They also asked the same question to 500 employed people aged 41 to 65, and 384 of them said that they used a computer at their work. So we're going to take a look at the age differences here. We have 25 to 40, which is 259 over 350 to get our proportion, and age 41 to 65 is going to be 384 over 500 to get the proportion. Looks pretty similar. Let's see. So the sample proportion is larger among older workers. The question of interest, however, involves the population proportions. Are the two proportions involved the population of all employees ages 25 to 40 and the population of all employed people 41 to 65? The question is whether the population proportion of the people agreed age 41 to 65 who used a computer at work is greater than the population proportion among those aged 25 to 40. So this is an example of a situation where we have two independent samples involving sample proportions. So we have P1, P2 are going to be the population proportions. P hat 1 and P hat 2 are the proportions of the two samples. X sub 1, X sub 2 are the numbers of individual in each category of interest in the two samples, and N1 and N2 are the two sample sizes. So the issue of whether the population proportion of older people who use a computer at work is greater than the population proportion of younger workers, we will begin with the null hypothesis, which states the populations are, or the population proportions are equal. The null hypothesis says that the population's proportions are equal right here, as the alternate says there are three. Either they're going to be, this should be, again, another mistake. These mistakes are driving me crazy. This should be smaller than, this is greater than, or not equal. Test based on normal distribution. The test statistic is based on the difference between the sample proportions. So when the size of the sample sizes are large, this difference is approximately normally distributed. So the test will be based on the normal distribution. So here we have the mean, the difference in the means, and we have the standard deviation. To compute the test statistic, we have to find out the values for the mean and the standard deviation of the sampling distribution. So the mean is straightforward. Under the assumption that the null hypothesis is true, we would get a difference of 0. The standard deviation is more involved because the standard deviation depends on the population proportions, P1 and P2, which are unknown. Under the null hypothesis, we will assume that P1 equals P2, so we can estimate P1 and P2 with the same value. So the value used is the pooled proportion. Pooled proportion. We're going to take x sub 1 plus x sub 2 over n sub 1 plus n sub 2. So the standard deviation of the sampling distribution, the standard error then would become, and remember, recognize this again, p hat times its complement, 1 minus p hat all over n1, plus p hat times its complement over n2. So when we do this, we can factor out the top, and we see that we take 1 over n plus 1 over n1 plus 1 over n sub 2, and then we're going to add them and then multiply it by the p hat proportion and its complement. So the test statistic is a z-score. So here's the z-score value. You're going to take the difference between the two sample proportions all over the square root of the sample proportion times its complement, and multiply that times our 1 over n sub 1 plus 1 over n sub 2. So the method for a hypothesis test for the difference of the population proportion will require the following assumptions. We have to have two independent, simple random samples. Each population is at least 20 times as large as the sample drawn, and the individuals in each sample are divided into two categories. Both samples will contain at least 10 individuals in the categories. So here's the steps. We're going to state the null hypothesis and alternatives. If we make a decision, we're going to choose a significance level. We're going to find the Z statistic, and we're going to compute the p-value. Here's our left-tailed, area to the left, right tail, area to the right, two-tailed, the sum of the area to the left and to the right. Then we interpret the p-value, and if we're making a decision, we will reject the null hypothesis if the p-value is less than or equal to the significance level, and finally state the conclusion. So here we have the same problem, the poll that we took 350 employed people, 25 to 40, and we also took 500 people aged 41 to 65, and we looked at who used a computer at work. So we can conclude that the proportion who use a computer at work is greater for those who are aged 41 to 65 among those aged 20 to 40. So is that true? So we're going to use the 5% confidence level. So first we're going to check the assumptions. We do have two independent random samples. The populations are more than 20 times the large samples, 20 times as large as the samples. The individuals in each sample are divided into two categories with more than 10 individuals in each category. And the assumptions, in fact, are satisfied. So let's go to our formulas. We're going to find our pooled proportion where we add these two together over the sum of the samples. We get 0.756471. So we're going to use that value down here for our p-hat proportion and times its complement. We have our 1 over 350 plus our 1 over 500. And then, of course, we have our p-hat 1 minus our p-hat 2. So after we do all of that, we get 0.9 or negative 0.94. So here's what it would look like under a normal curve. Using this table or the technology, we find the area to be 0.1736. So since the p is bigger than 0.05, we cannot reject the null hypothesis at the 0.05 level. So we cannot conclude that the proportion of workers aged 41 to 65 who use computer is greater than the proportion among 25 to 40. We can do it using technology also. So you can look here to your 2 prop z tests, put in your values, and then you can get your p-value here. You can also do it with your mini tab. Performing a hypothesis test for the difference between two proportions using the critical value method. So again, we have some of the similar steps. We're going to state the null and alternate hypothesis. We're going to choose a significance level, find the critical values, and use our test statistic. Here we have Z. Determining the same areas for rejecting a null hypothesis. We have our left-tailed, our right-tailed, and our two-tailed, and state the conclusion. So here we have a total of 82,486 accidents involving drivers aged 15 to 24 years old. 4,243 of them, or 5.1%, occurred in a driveway. Out of the total, 219,170 accidents involving those drivers between 25 and 64 years, 10,701 of them, or 4.9%, occurred in a driveway. Can you conclude that accidents involving drivers 15 to 84 are more likely to occur in our driveways than accidents involving drivers age 25 to 64? So we've checked the assumptions. We have two independent samples. The individuals in each sample fall into two categories with at least 10 individuals in each category, so our assumptions are satisfied. And the null and alternate hypothesis are these two would be the same, or we're looking at whether or not this one is greater than the second. So we do our pooled proportion again, just like we did before, and our Z statistic, just like we did before. And then these are all of our reminders over here of what we have given. You should always have those written at the top. Now, because this is a right-tailed test, the critical value for the area is to the right of 0.05. The value of Z alpha is 1.645. So we're going to reject the null hypothesis if Z is bigger than Z. Z1 is bigger than Z2, or Z2 is bigger than Z1. Let's take a look and see what it says in the book. All right, let me see. Crazy stuff here. So I'm going to go to the book and we're going to take a look to make sure that they have it correctly in here. And we are using our 11.2, checking our understanding. Yeah, so we're looking at the value of, where was I at? Right here. So we're looking at these values, and let me make sure I have the right, uh-oh, forgot to turn off my phone, so just ignore that. Okay, so let's go back and just read what it says. So can you conclude that accidents involving drivers 15 to 24 are more likely to occur than drivers aged 25 to 64? So we're going to say that we're looking at the P1 is greater than P2 again. So let's go back to our slide. Here we go. So we want to know if Z1 would be greater than Z2. And because Z is 2.95 and Z alpha is 1.65, then we're going to reject the null hypothesis at the 0.5 level. So we can conclude that accidents involving drivers age 15 to 24 are more likely to occur than accidents involving drivers 25 to 64 in the driveway. So that's kind of funny to me. All right, so we should know how to perform a hypothesis test for the difference between the two proportions and how to perform a hypothesis test for the difference between the two portions using the critical value. Okay, so that's 11.2. Next one will be 10.3, and we'll talk to you soon.